Hello, everybody. I'm glad to introduce our last speaker of this morning session. Roberto Buizza will talk on numerical modeling applied to weather prediction and climate.
Okay, very good. Thank you very much. Thank you for having invited me here to mix with people doing very theoretical studies. What I will try to do is to try to connect things that we have heard during the week. For example, singular vector techniques used to identify instabilities in systems or stochastic modeling to some real application, which is essentially numerical weather prediction as done at the European Center. I left the European Center about a year ago. I'm now working more on climate. I'm starting a new group of people at Scuola Universitaria Sant'Anna of Pisa, with Scuola Normale Superiore, and another Scuola Superiore in Pavia. So, but I'm going to talk about essentially numerical modeling applied to weather prediction and climate studies. So one of the reasons why weather prediction has changed completely in the past 25 years was the fact that if we look at, for example, forecast busts, we were used, say, in the 80s and 90s of very many forecast busts. So forecast bust is essentially a case where 3 to 5 days before the event, we were really not able to make any prediction of what was going to happen. So a lot of people in the 80s and early 90s was starting to ask the question, well, how can we deal with forecast busts? Can we do something to reduce them? The red curve is the number of forecast busts in the operational forecast of the European Center. So I just wanted to show you this slide essentially to motivate the fact that we are at the beginning, at the end of the 80s, early 90s, and the problem is very much there. So with 2-3 forecast busts a month, which is a big number. Now, the other point that I want to make is that, so I'm going to talk about application to a system which has a lot more degrees of freedom of a system that we heard a lot of the talks this week. So I'm talking about NWP and climate models that have an order 10 to the 6 to 10 to the 9 degrees of freedoms. So any problem that we're trying to approach for this type of model are very complex, also because you cannot really do much analytically, but even numerically, it's very challenging to essentially decide how to apply the ideas that might be simple and might be very easy to develop in systems with 2 or 3 degrees of freedom, but it's a different matter if you want to apply the same idea to very complicated models. Okay, so the way we link dynamical systems like Lorentz, 3 degrees of freedom, or the Lorentz 96, order 10 to 100 degrees of freedom to the real world is actually not trivial at all. But still, there are a lot of ideas that come from dynamical systems that have been used and are used in complex systems like NWP or climate studies, which are very relevant. Okay, for example, the fact that in the Lorentz system we see sensitivity to the initial conditions, to very tiny perturbations, and how they evolve on the attractor can actually be seen in the real world. On the right-hand side, you see on the top left what happened on the 4th of December 1999, a strong storm affecting Northern Europe, and the first map on the right is the forecast, the operational forecast that was issued at that time. 5.5 day forecast, which completely failed to identify a system. The other maps that I'm showing are actually forecasts started from very slightly perturbed initial conditions. So it's essentially mimicking what Lorentz did in the three-dimensional system, where he showed that in some cases you have a lot of sensitivity to initial conditions. On the right, you actually see with the real system. The forecast, all the maps that I'm showing on the right, are all 5.5 day forecasts started from initial conditions which were slightly perturbed using very tiny perturbation which were mimicking analysis error. I'm going to talk about 5 main topics. First, remind you how we do weather prediction. Then I will talk about ensemble methods. Then stochastic modeling, how we're using stochastic schemes to actually improve our predictions. Then say a little bit about how we apply all these techniques to climate studies. I mean, I will leave you with a few open questions. So just to remind you that NWP is essentially an initial value problem. We treat it as an initial value problem, which means we're trying to define initial condition which should be as accurate as possible. And when we have got the right initial condition, we integrate the equation of motions, where on the right-hand side here you see the tendencies due to the dynamics, the physics, and another term that I used to represent the stochastic perturbations that I will talk later. So the way we think of numerical weather predictions is that we need very good initial conditions as a starting point. It's essential to make a good forecast, and then clearly we need a very good model. Okay, the way I am represented it here schematically is the way we do it at the European Center in ensemble mode, where instead of doing just one forecast, we do n forecasts, j going from 0 to 50, where 0 identify an unperturbed forecast, and all of the initial conditions of this forecast are generated by a best estimate, a linear best estimate, which is computed using a high resolution dimensional variational system plus some perturbations. The tricky aspects of NWP are the computations of the right-hand side tendencies of equation of motion and temperature due to the physical process. This is what makes NWP extremely difficult. This is what makes forecasts going wrong at one point when we integrate the equation of motions. The second point that I want to point out is that clearly this type of equation, as I said, degrees of freedom 10 to the 6 to 10 to the 9 are solved numerically, so we need to make some approximations. They are solved on a grid, which means that we cannot resolve all the scales of a model. We have to define a certain grid size, and in some way we are solving the equation of motions in boxes with a size which depends on the resolution of a system. This again introduces approximations, and it can be a source of errors. Yesterday we were discussing resolution and scales and models not being able to resolve all the scales of a system, which is a point I want to make showing you this graph. What you see in black is a very good estimate of the kinetic energy of the atmosphere. It's a simulation with a European Center model run at 2.5 kilometers. Say it's our target. In blue and cyan and red, you see 3 different model versions of the European Center model. The red one is the current operational model. What we want to do is have a model simulation be as close as possible to our target, our black line, which is very close to observation. And what you can see is that even when we run a model with a resolution of 10 kilometers, which is this line, now the spectra, the kinetic energy spectra of our model is not exactly on top of the kinetic energy of a high resolution simulation, which represents observation. So even when we are thinking of models with a resolution, when we are using models with a resolution of 10 kilometers, there are approximations which makes the model not capable to resolve in a good way all the scales. We estimates put the scales that we are able to resolve correctly to about 5 times the grid spacing of a model. Again, it depends very much on the type of a model, on how stable it is, on the numerical methods used to make the integrations. Here what I put are the total spectral wave numbers. So for the European Center model at 1279, the resolution is about 10 kilometers. Yeah. So the different curves are different versions of the European Center model. This one, the blue, is the operational model which was used up to 2016. It had a spectral resolution of 1279, but the grid on which the physical processes were computed was a so-called linear grid, which had less grid points than the cubic octahedral grid used in the red simulations. Okay? In cyan, you see a model which is similar to the blue, but has 2 times more wave numbers. But again, so it has double the number of waves in spectral space. The European Center model is a spectral model, but it has kept a linear grid. So the number of grid points is double the number of grid points for the TL1279. But because of the numerical instability of the scheme, which is based on a linear grid, it's not, and the need of using a lot of a stronger horizontal diffusion, the result is that the spectra are very far from the spectra, our target spectra, which is the black. By changing in 2016 the grid used to solve the physical, to compute the tendencies due to the physical parameterization, the model is capable now to use less horizontal, less diffusion, it's more stable, and so the spectra is much closer to the target. And the way we do forecast is essentially to take a first guess, which is a short-range forecast, collect as many observations as possible, estimate initial conditions with a data assimilation procedure, and then do the next step of a forecast model. Okay, so one of the main ingredients, as I said, it's an initial value problem, so we need to try to estimate the initial conditions at our best, which means we need to try to assimilate as many observations as possible. We need to have a very good model, and so that we can reduce the initial error of a system. And in fact, in the past 25 years or so, thanks to advances in the observation systems, thanks essentially to the use of very many observations from satellite, we are now able to collect order 600 million observations a day. Of them, we select about 60 million, so about 10% of them are used. 95% of these observations come from satellite, and this clearly has helped us reducing the initial error of a system. Okay. Now, if I think back to what I said, which is using development or methods tested with simple system, one of the first things that we've been using and taking from simple system were our data assimilation technique, which is how can we merge in an optimal way information coming from a first case forecast with all the observations that we are collecting. This is an easy problem if you have a 2-degree system or a system with very few degrees of freedom, but when you have to do it with a system with 10 to the 6, 10 to the 9, 10 to the 10 degrees of freedom, assimilating 10 to the 6 observation is not trivial at all. And the way we manage to advance is to use variational methods. Variational methods which essentially work in the following way. There is a first case trajectory in phase space. I'm representing it here in one dimension. We have a set of observations which lie on an observation space. For example, we might have observations from a satellite coming in terms of radiation, but our model is formulated in terms of state variables like wind, temperature, pressure. So we need, first of all, to project from the model space into the observation space. We compute a difference between the observation and the model projected into the observation space. And the idea of data assimilation is to try to reduce the distance between all these points, the projection of a model and the observations, and identify a correction to the initial state so that our trajectory go closer to the observations when again we project it on the observation space. Yeah, this is the way it's done at the European Center is by using a four-dimensional variational system that allows us, in fact, to assimilate observations over a time window and not just at one point only. Now, one of the complications of doing this, again, with this very complex system is to define exactly what type of weight we want to give to the model, first guess, the weight we want to give to the observation, to the observation down here, and if we want the weights that we might want to give to estimate also some parameters in the model. So now, for a minute, forget this term. One of the big problems in data assimilation is exactly how much weight do I give to my model compared to the weight that we give to the observations. Again, there are complex techniques to estimate these weights. The way we do it now at the European Center is that the model weights are estimated in a flow-dependent way using using statistics based on past data assimilation run in the past 3 days. And the observation weights are defined using statistics of the instruments themselves. Further complexity arises when we're trying to identify the initial condition when we're dealing with two media with very different spatial and time characteristics, for example, the ocean and the atmosphere. Today at the European Center, there is a weakly coupled data assimilation that uses observation, that uses ocean, atmosphere, land, and sea ice. Again, the problem there is that there are two media with different time and spatial characteristics, with different number of observations, with very different observation errors. So again, a big question is how do we merge together all this information, giving the right type of weights to all this type of information that we are collecting. And one of the questions that we are still wondering is how much coupling we need to do in these techniques in the formulation of the minimization problems. What you see here is an estimation of a correlation between ocean states, which are the one on this side, and the atmosphere and the atmospheric states in the vertical. Going from model level 0 to the top of the atmosphere, and in the ocean going from model 0 down to the 75 levels of the ocean model. So as you see, there are a lot of, the correlation matrix is essentially diagonal, but it's not completely diagonal because there are some interaction between different variables and different levels. The way we are estimating this type of matrices, which are used in a weakly constraint for DVAR that we're using now, is using ensembles of past states and try to identify how much we should really connect variables in the two media. So weather prediction is an initial value problem. One of the big challenge is to estimate the initial state of this complex system so that we can do very good forecast. up to 1990, up to the beginning of the 1990s, the problem was approached in a deterministic way. The idea was that we try to estimate one single initial condition, we do one forecast only. But as I said before, people realized that in this way it was not possible to estimate when we could have a so-called forecast pass, when the system could go through a period when all the forecasts were failing. So we started thinking, okay, how can we move from this approach based on a single deterministic initial condition and model to try to say something about the probability that the atmosphere is less predictable, that in the future we might have a forecast pass. What I'm showing here are the anomaly correlation condition actually for a geopotential height at 500, so it's the flow at 5,000 meters height, it's the large scale, the synoptic flow, 5-day forecast. Just 1 year ago, it's a series of forecasts from 5 NWP centers, including the European Center. And as you see, first forecast bust occurs still today. This is a 5-day forecast with an anomaly correlation below 0.6, which is extremely rare. On average now, a 5-day forecast has an anomaly correlation of about 0.85. So the thinking at the time was that instead of doing one single forecast, maybe the way to move forward is to try to generate an ensemble of forecasts and make statistics on this ensemble of forecasts so that we could estimate whether the trajectory would stay close together or would diverge a lot, and use the information about the divergence of these trajectories to tell us something about whether the conditions we are now lead are more or less predictable than in other cases. And here are examples of forecasts issued today at the European Center. The European Center now issue all forecasts based on ensembles. You see a strike probability of Hurricane Dorian. You see an ensemble of forecast of a propagation of a Madden-Julian oscillation of a organized convection in the tropic. You see an ensemble of forecast of SST, over 12 months, ensemble of forecast of SST in the El Niño area. But if we go back to the end of the 80s, beginning of the 90s, the question was, how do I design this ensemble? I have a system which is very complex. I have a system which has a lot of degrees of freedom. I cannot afford to do hundreds or thousands of forecasts. I might be able to afford to run only few of them. So how can we estimate the initial state of a system and its uncertainty? How can we evolve then this PDF in forecast mode? There were trials to try to integrate the so-called the Liouville equation that describe the evolution of a density function of a state variable of a system. But no, there was, for example, a couple of work by Martin Ehrendorfer in 1995. The problem is that integrating this equation to try to evolve it in forecast time was extremely expensive. So Ehrendorfer managed to do it with the three-dimensional Lorentz system. Here are some results from his work. But he clearly said in this work that the high dimensionality of a phase space encountered in case of realistic meteorological models seems to prohibit this approach. So there is no way, and immediately people realized that there was no way that one could take the Liouville equation and try to evolve this density function of forecast state. So people had to think about ways of estimating the initial, or some points on the initial PDF, evolve them in time, and use the forecast time to estimate the probability of future weather events.
So which way was he using to solve the equation? It was a
He did it numerically. Yeah, 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 yeah. So if we now think again the process, the NWP process that I presented before, I said that we need initial conditions. These are estimated using observations and the first guess, and then forecasts are done using a model. Clearly, if we want to estimate the initial uncertainties and the forecast uncertainty, we need to try to take into account all the possible sources of forecast error. So we need to think about taking into account observation errors coming from the fact that observations have different characteristics and sample the globe in different ways. We need to take into account model uncertainties. I said that we are resolving the equation on a finite grid. We make approximation when we define our parameterizations. The physical terms are the most difficult one to do. And then I talked about a data assimilation procedure, again, to get to identifying an initial state, even with a most sophisticated system like a four-dimensional variation, you need to make some assumptions. So for dvar, it's based on assumption on the statistics that you use to correlate the errors between the different variables. You have to make assumptions on how you go from your model state, from your state variables into the observation state. All of these terms can lead to approximation and they need to be taken into account. In the early 1990s, experiments like the one that I'm showing were done to identify which were the first, the leading sources of forecast error. What you see here on the right are differences between, for one case, of forecast done from the European Center model starting from the European Center analysis. Sorry, this is the error of a European Center forecast. Okay, just to give you an idea of how big it was. And then on the top, you see the difference between two 5-day forecasts run using the UK model starting from the UK initial condition and the ECNWF model starting from the ECNWF initial condition. As you can see, the divergence between these two forecasts was comparable to the error of one of the two forecasts. The question was at that time, well, does the divergence, does the error, does it come mainly from errors in initial conditions or in the model? Where should we focus if we need to design an ensemble? We are, as I said, at the beginning of the 1990s, people didn't have a lot of experience didn't really know how to deal with model errors. There were some people who were trying to do forecast using 2 or 3 different models. But essentially the question was, where should I invest more to try to estimate the evolution of this PDF? On the bottom you see 2 forecasts running from the same initial condition, in this case the UK initial condition, but using 2 models, UK and ECNWF. And on the top right you see 2 forecasts run using the same model, EC, but starting from 2 initial conditions, the UK and the ECNWF forecast. So this type of analysis, in the paper that we wrote at that time, we look at many cases, we did statistics. It was clear that in the first forecast range, in the short forecast range, day 3 up to day 5, the initial error, the initial uncertainty were the leading one, the one that were generating most of the divergence between the models, most of the errors when we were comparing to analysis. So at the beginning of the development of this ensemble method, a lot of efforts was put in trying to define the best way to design, to estimate these initial uncertainties. Now, looking back at the time, essentially 3 types of approaches were followed. There were people who were trying to design methods inspired by the Kalman filter. An example is the Canadian ensemble, which went operational in 1995. Then there were people like European Center and Washington who went for a so-called reduced sampling approach. The idea is that I don't need to, well, first of all, there were experiments done by adding simply random perturbation to initial condition, and these were not growing. So they were not giving any information at all about the possibility that the forecast could diverge. So it was clear that one had to be smarter in defining the initial state of these ensembles. And at NCEP and at the European Centre, we tried to identify a clever way to define initial perturbations. And I will illustrate what we did at SNWF. And then there were other people who tried to build ensembles using lagged forecasts. So using forecasts started over a period of time. For example, 3 days ago, at that time, forecasts were issued every 24 or 12 hours. So if you start collecting forecasts issued on the past 3 days, if you have a forecast every 12 hours, you might end up with a number of order 10. But again, that immediately it was clear that because you're mixing younger and older forecasts, the older forecast being worse, it wasn't really giving any good information. At the European Centre, we actually look at work done by people with studying dynamical systems or perturbation growing in simple systems. For example, someone mentioned Brian Farrell and Ioannou in the first day that we were here, and they were some of the first people working on the idea of a singular vectors, which is try to identify perturbations of a system with a maximum growth rate over a finite time interval. So our problem is forecast over a finite time interval, 10 days, 15 days. So we are limited in that, our perturbation analysis. We want perturbation that would essentially grow and spoil our forecast over that time interval. And the way to do it is to use singular vectors. So here you see some maps of singular vectors. These are very localized structure. How are they computed? Well, the idea is that you take the nonlinear equation of a system, you look for solutions around a trajectory. So you look for small perturbations at prime. You linearize the model equation, and you define so that you can compute how a small perturbation would evolve in time by solving a linearized version of equation of motion of your model. Once you have done that, you essentially want to try to identify the perturbation that over a time t would lead to the largest growth in terms of a certain norm. In our case, we decided to use total energy as the norm. So the problem is to find the directions at prime in this 10 to the 6, 10 to the 8 degrees of freedom that could lead to the maximum amplification of a norm. Z prime at time t can be computed by a linear integration of a model equation starting from initial condition Z prime not. And if you use the definition of an adjoint operator, you essentially what you end up needing to solve is an eigenvalue problem, where you're looking for the eigenvectors with the largest eigenvalue of this combination of operators. There is a norm at initial time, there is a norm at final time, and there is a linear propagator and the adjoint propagator that allows you to move back and forth in the time interval in which you're working on. So this was for one example. This is one example of techniques and methods taken from people working with much simpler systems but applied to a much complex model, which is the NWP model. First problem is, for example, how do you write the tangent linear and the adjoint of a full GCM? A GCM is 1 million lines of code. You cannot really write down the adjoint equations and code the adjoint equations of this model. The way we have done it is that you need to think of each line of the code as essentially as a linear transformation, where now you take the nonlinear. If you have a line of code which includes some nonlinear term, first of all you linearize it, then you write it as x equal a y, where a is a linear matrix, and then you need to write a similar line of code that would do the adjoint computation of that. In this way, we managed to compute a singular vector. Singular vector, as I showed earlier, are quite localized structure. You see them in the vertical. They identify the fastest growing perturbation in the system. Why do we want the fastest growing perturbation of the system in this case? Because we are interested in identifying the components of initial error that could lead to a large forecast error at finite time. So we want to look at whether there are directions in the system along which, if I have an initial error, I can spoil my forecast. If I don't find any, it means that the situation is predictable, the divergence between my ensembles remains small, and so I can say something about the forecast skill at forecast time. If instead I find directions with a large amplification rate, with a large eigenvalue, it means that if I have an error in that direction, I can spoil my forecast. So the only thing that I can say is that this is a more unpredictable situation. I might have a large error. Okay? This is how we thought of defining the system. Okay? Now, one of the problem of this type of approach is that there was very little connection between the data assimilation problem and this perturbation. So the perturbation that we were computing at that time, in the early times of the development of the ensemble, knew nothing about the fact that certain areas of the globe were observed better than others, that we were having less errors in some region. For example, over the land, typically you have a lot more observation, a lot more accurate observation than over the sea. So there were some work done in trying to introduce information about the fact that certain areas of the globe were known better than others in this by changing the norm used at initial time or at final time. For example, we tried to estimate, to use as initial time norm a norm computed using data assimilation, but it did not actually work. So at the end, we decided that the best way to take into account observation errors and the fact that the globe is observed in a different way was to add a second set of perturbations to define the initial state of a system. And this was done by using an ensemble of data assimilation, where we would compute a set of an initial condition using perturbing the observation inside each time window, so that we would have not just one estimate of initial state of a system, but an ensemble of them. And then we would have a singular vector that would identify perturbation that might grow and spoil our forecast. And by combining them, we could take into account both sources of error linked to the dynamics of a system and to the observation, and to the type of observation we were using. What you see here is an example of a type of perturbation you generate with this ensemble of data assimilation. As you can see, these are very different structure from the one that you get with the singular vectors. They are less localized. They are much smaller scale. They don't show this vertical teeth with height, which is characteristics of structure that can grow using baroclinic instability. So We went from a deterministic approach to a probabilistic approach using ensemble methods. And up to now, we have been focusing mainly on the problem of the estimation of initial error. And we did it using singular vectors or a combination of singular vectors and ensemble of data assimilation. So far, our model is still, our ensemble system is still lacking any simulation of model uncertainties. And in fact that we were lacking the simulation of model uncertainty was clear, for example, in this work. We are talking about, we are in 2005, it's comparison of free ensemble system, European Center in blue, Canada in red, Washington in black. The divergence among so I'm trying to use the divergence among my members as a predictor of the forecast error. This would work if, on average, over many cases, the divergence among my forecasts would be similar in amplitude to the error of my forecast. And as you can see here, now this works quite well. So I'm comparing the dashed and the black lines. It works quite well up to forecast day 5. But doesn't work well beyond that. Now, if you think about what I showed earlier, we said that the initial condition errors were dominant in the short range, but at one point, model uncertainties were starting to be important. So again, this is work done towards the end of the 1990s. People started thinking, okay, how can I represent errors in the model due to this, to the parameterization of these processes? Or due to the unresolved case, this case that my model doesn't see because I have to solve my model on a finite grid with a finite resolution. And here, we borrowed and we took ideas and technique from stochastic modeling. So the idea is, suppose that we have written our model, we have a set of parameterization, we try to simulate how a certain physical process would change the tendency, for example, convection. We know that our convection scheme has been built using certain approximation, and there are parameters in the model that we estimate as best as we could, but we know that there are some errors there. So why don't we insert in the right-hand side of the equation that we are integrating an extra term where we try to put in some extra tendency due to the fact that we don't really trust our physical parameterization scheme, so we perturb the tendency we compute from these schemes by a set of random numbers. They are actually not completely random. We can introduce a structure in this number. We can introduce some spatial and time correlation structure. And then why don't we also introduce another term on the right-hand side that simulates the fact that because we have truncated the model at a certain resolution, we are missing the interaction between the smallest case, which are gone, and this case that the model sees. So these are the two schemes that were developed and introduced. One was called stochastically perturbed parameterized tendency, and the other one stochastic kinetic backscattered scheme. These two schemes proved actually to be very, very valuable and very useful. What you see here is the impact of having or not having these schemes simulating model uncertainty on the scale of forecast up to 30 days. So the fact that it's negative means that it has a strong positive impact. If we didn't use the schemes, we would have under-dispersive forecast systems. Okay, I just show you a couple of slides on how we can then, these techniques develop to initialize NWP system and to assess the forecast key, so assess the uncertainty in the forecast, are now used, for example, in climate studies. And I want to mention a data assimilation a climate reanalysis that we completed 3 years ago within a European Union project called ERA-CLIM2. The idea was that we wanted to simulate, to reconstruct the climate from 1900 to today by using only surface observations. Why only surface observation? Because we didn't want to have results affected by the fact that the observation system was changing dramatically. And the way we did it was to essentially run an ensemble of data assimilation. So we brought together ideas from the ensemble world. Each member of this data assimilation included some stochastic term to simulate model errors. The observations were perturbed to take into account observation uncertainty. And the results is a 110-year reanalysis, which includes 10 members. And these 10 members can be used to estimate not just the mean state of a system. Here I'm representing the average mean sea level pressure over the northern hemisphere, but also by looking at the spread between this 10-member ensemble, try to get to assess the uncertainty in the past climate. And I conclude with 4 points, 4 questions that on which people are working on now. So the first one is on the PDF evolution. Now we are all the world is running ensemble system to do short range, medium range, monthly, seasonal prediction, climate projections. The question is, are this ensemble method that we developed the best way to estimate the evolution of a PDF of a PDF? Or can we go back now that we have computers which are much more powerful than the ones we had in the 1990s? Can we go back and take again the Liouville equation and see whether we can redesign the problem using starting from the Liouville equation? Initial conditions. No, we've moved from having models which represented only one media atmosphere to using coupled system to do also the short range weather forecast. Now the question there for data assimilation is which level of coupling do we need to introduce in this data assimilation system? Do we need to have couple covariances? Which level of coupling do we need? Model error. Model error is still simulated using these rather simple stochastic schemes, either the backscatter or the SPPT. The question there is, can we design better methods to estimate the model errors to take into account these ensembles? And then if I think about the climate projections, all this machinery was really developed for NWP problems. And it has simply been taken and applied to climate projections, so runs going to 50 years, 100 years. Are they the best way to try to estimate the climate projection? Or maybe for the climate problem, we need really to think again and design a different way to estimate the uncertainties in the climate. Thank you very much.
Time for questions.
So on the last, on the point that you made, don't you think that for climate problem, the initial condition probably is not so important, and what would really should be done by data assimilation is to do parameter estimation for the subgrid processes?
Yes.
You could include those in the unknowns rather than just the initial condition. It's only a few of them.
Yes, I agree. I agree that for climate projection, the initial state is maybe less important. But what, for example, I would like to see is that we use this Sant'Anna reanalysis to test how our models behave over 20, 30 years. It's true that the climate problem is not an initial value problem, but I would like to see how good are our climate models if we start them in 1900 in simulating the climate that we see in 1940, and then we initialize them in 1910, and we try to reproduce the system in 1950, no? At least to see whether we are really able to say something about the next 20 or 30 years, which are the years where we are saying that extremes will be more frequent, that Arctic might melt a lot more. Well, I would really like to see. So it's true that it's not an initial value problem, but now that we have this 100, NCEP has done 150 reanalysis, let's use these states to initialize and test how good our climate models are, and use them to diagnose whether there are parts of a model which needs to be changed or retuned or fixed.
Yeah, my question was about the same. So if I understand well your answer, you want to use the weather model and all what goes with the weather model to do climate prediction in order to assess the quality of climate models. Is it what it's what you said?
Yeah, in fact, this is what a version of the European Center model is used to make CMIP6 integration. Clearly, we need probably, there are parts that are important for the climate model which are not maybe in the NWP model, but I would definitely try to converge and use the same type of model for NWP and climate studies, so that we can test the same model can be tested on shorter range, on monthly, seasonal, 5-year forecast. Use all this reanalysis to see whether the model behaves well, and then run them to do climate projection for longer time. I think if we use the same model, we can learn, no? We can improve them by testing it on a shorter range and then using it longer, and vice versa. If we take the NWP model and we try to run them for 20 or 30 years, we can learn whether they have some errors in the parameterization that lead to strong biases. The ocean models which are used now drift a lot. We know because we have been trying to do this climate reanalysis, and we have seen it by running a climate reanalysis. So we need to find a way, improve the ocean models so that they don't drift so much.
Hi Roberto, thanks a lot. A comment on the stochastic parameterization, which I think is a really hot topic, and also it's a good, connects well to people more interested in more abstract argument. I mean, in statistical physics, people will call it, this has to do with operation of coarse graining. Of course, when you construct something like this, you have to tune the quantities to represent as well as you want something. Yeah. Okay. Something I would like to bring to your attention is the fact that, as an example, it might be that if you tune your parameterization to optimize, as an example, the mean or the variance, you might miss certain extreme events you want. I mean, so there is a recently published paper, first author is Guanan Hu in Chaos, where is a student from Hamburg, and we studied exactly this problem, and we showed that basically by if you want, by overfitting, but anyway, by fitting your stochastic parameterization constructed by basically by an ad hoc procedure, you might get very well, extremely well, the bulk of the distribution, but you might miss, I mean, greatly the not the outliers, just the extreme events as defined as events, I don't know, above. So this is something that I think needs to be taken into account when constructing this guy. So what is our target? What is our cost function? And I talked to Magdalena, your colleague at ECMWF, about that, and she's quite interested. I think, let's say that we have to think about how to tune these objects, because the risk is that we miss what we are most interested in.
Yeah. No, unfortunately, so far, the stochastic parameterization, which are added now almost to all the ensembles, have been like bolted on, while we have been discussing a lot at the European Center on changing completely the way parameterizations are developed. One should really, when you develop a parameterization, think about, I'm using my model to evolve a PDF. And I develop a parameterization scheme thinking I'm going to use it in ensemble mode. And I want it to be able to give me the mean and the variance correctly. While this is not how it is. At the European Center, we have been trying to go along that line, and it's extremely difficult. The techniques based on the adjoint have been tried to estimate parameters and how to perturb parameters. But again, the minute you start identifying the parameters that drive a parameterization, you get to 50, 20, the possible combinations. So one really needs to rethink of the way you code a model, depending on whether you're going to use it to evolve a PDF or to do single trajectory. And we are not yet there.
Okay, let's thank Roberto again. And with this, we close this session.